Hi and welcome to part 4 in my continuing mechanics series, and today I'm going to talk about definitions of strain and how we can calculate strains from deformation gradients and stretch tensors specifically. So let's start this by talking about first something that's related to polar decomposition. So this is a step that is needed in order to calculate strains later on. So I'm going to first talk about how we can perform the polar decomposition in theory. So often it's well known what the deformation gradient is, but we also know that deformation gradient is decomposed into a stretch tensor and a rotation tensor, or as a rotation tensor and a stretch tensor. The question here is, how do you calculate this rotations and the left and right stretch tensors if all you know is the deformation gradient? And there is pretty easy ways to do this, and I'm going to talk about that here. So here is again the decomposition of the deformation gradient into stretch and a rotation. It turns out, of course, as we talked about earlier, if you form the quantity F transpose F, you end up with a quantity that's called U squared that does not depend on rotations. And this is the right stretch tensor. And what we want to calculate here is U, not U squared. So that would be the square root of F transpose F. And it may seem kind of weird. How would we possibly calculate that? And the way we can calculate that is using the power of the spectral decomposition. So we want to calculate U again, and we know that U squared is symmetrical. So we know that the eigenvalues and eigenvectors of U squared, which is easy to calculate, it's simply F transpose F, can be written in a spectral form as this. So they're lambda I squared here, or the eigenvalues of this U squared tensor. So lambda I squared are the eigenvalues of U squared. And once we know that, we can remember that you can operate under the summation sign here. So when we do the square root of U, all we have to do is to take the square root of this quantity lambda I squared. So that becomes lambda I. In other words, U is given by this equation down here. Very simple to calculate once we have F, obviously. And that's kind of the whole point of this. Once we have U and we have F, we can also very quickly calculate R, and we can calculate V, the rotation, and the left stretch tensors. So that's how you calculate these things in practice, and that's good to know because this is needed for many calculations where we have the deformation gradient, but we want to calculate strains, for example. Now, a strain itself cannot depend on the deformation gradient because a strain does not depend on rotations. It can only depend on stretching. In other words, the strain can only depend on U or V. And there are different ways this can happen. If we have a strain equation here where the strain is given by a function of the stretch tensor U, we need to figure out how we do this, right? So this is, in general, the strain is some kind of function of U. What we can do here is again use the spectral decomposition, and we can use this function. We put it to operate only on the principal values. So F of lambda I is this equation that we can choose ourselves to get the strain equation. And capital Ni are simply the eigenvalues, eigenvectors in the reference configuration of the deformation gradient itself. So this scalar function here is very important, and it gives us this strain itself. But there are 3 rules that this scalar function F needs to satisfy. First of all, we want the strain to be 0 if there is no deformation applied. And we can achieve that by setting the restriction that the function F needs to be 0 if F when the value is 1. So F of 1 equal to 0. The second one is that we want the strain at large deformations, which is what we're talking about here, to be the same as the traditional strain definitions at infinitesimal strains. That is, we want the more general equation to become the basic equation at small deformations. And we can achieve that by setting the derivative of F to be equal to 1 in the undeformed configuration. So F prime 1 has to be equal to 1. And finally, we want the strain to monotonically increase as the deformation increases. So these are the rules that we want to satisfy. And Here are two common reference configuration strains. There are many others. In fact, there's an infinite number of strains one can define. The green Lagrange strain has this scalar function f of lambda that's shown here. And this gives you this tensorial equation for the strain, the tensorial strain itself as a function of the U tensor. And the bottom here is another strain called Biot strain, and this has this definition at the bottom here. Most of the time, however, we often work in the current configuration when we do finite element simulations. And in that case, we have the very similar strategy. The current configuration strain has to be a function of some kind of the left stretch tensor V. And we can achieve that by defining a function f that operates on the principal value, the eigenvalue lambda I here of the V tensor. And ni, or simply the lowercase ni, or the eigenvectors of the deformation gradient in the current configuration. And we will need the same three rules on this f function in this case as we had in the reference configuration in order to satisfy what we think of as a good strain. To make this more specific, here are the perhaps two most commonly used strain measures that are used. The nominal strain is sometimes called engineering strain, and the true strain is sometimes called Cauchy strain or logarithmic strain. Here are the scalar functions that define these tensor products and the actual tensor equations itself. So these are tensorial strain, which is calculated in these ways, and these are often available through finite element programs. And this is what most people think about when they talk about strains in different ways using the tensorial notation. And what I've shown here is that using continuum mechanics, we can calculate strains from deformation gradient by switching over to the stretch tensor and working a little bit in these spectral representations that I talked about. That's all I want to talk about strains. We're going to, in the next part of this series, we're going to switch over to stresses. If you have any questions so far, you can ask them below.